Okay, hello everybody and welcome to class today. Looks like it's time to get started, so hopefully people will continue to join. So today we're going to take a little bit of time to finish up hypothesis tests, and then we'll be talking a little bit about time series today. So this is going back to lecture 7 that we started on Tuesday, and I'm going to not go over confidence intervals in class, but I'll leave this for you to read about. So there's just a little short section here about confidence intervals, which is pretty straightforward. So read through that. But I thought we would get started today looking at part 2, which is on 2 sample hypothesis tests. So you may remember last time we started talking about statistical inference and setting up hypothesis tests from a data set to test a hypothesis about the population. Now, what we did last time was on statistical inference for a single sample. However, a lot of times in statistics, you're really more interested in making comparisons between 2 different populations or between 2 different treatment groups. So probably even more important is our 2 sample hypothesis tests. And these generally come, there are a lot of different variations, but I think the main 2 to kind of be aware of is, first of all, if your variable of interest is quantitative, so you're recording a numerical measurement, you often want to compare the means. I'll call this mu A and mu B of 2 populations. So for example, here your null hypothesis would be the mean in population A equals the mean in population B, and your alternate would be that they are not equal. You could also have, a one-sided test. This is just how the 2 sets be set up. And then also if your variable of interest is categorical with 2 categories, so, you might be looking at how many people got sick, or you might be looking at gender or along these lines, something that can be where you're interested in the percent of a population with a certain characteristics, then the basic hypothesis test that we would perform there would be for 2 proportions. So PA and PB would be the proportions of the 2 different populations, A and B. Null hypothesis, PA equals PB, alternate, third. Okay, so remember, and this is the same as for 1 sample hypothesis tests, mu A, mu B, PA, and PB, all of these parameters that appear in the null and alternate hypothesis refer to the population parameters. So we will be, and again, sorry, no activity today. I felt like there was a lot to cover this week and I didn't manage to squeeze in time for the activities, but hopefully next week when we do linear regression, we'll do an in-class activity for that. So sorry. Okay. So the hypotheses are always about the population parameters, and we will evaluate whether there is significant evidence for it using sample statistics, using the sample mean of the 2 populations, the sample proportion of the 2 populations. So we want to, from these sample statistics, make an inference about what's true for these population parameters. Okay, so let's let NA and NB be the sample sizes from populations A and B respectively. Okay, so let's start off with the 2 sample hypothesis test for comparing 2 means. So when we have 2 independent samples, we compare the means with the 2 sample t-test. So last time we talked about z-tests, and then we talked a tiny bit about t-tests, and we said, yeah, I want to do a t-test because it's more robust to small sample size. So this is what people do in practice. So I thought we would go over this in terms of how to do it in R and how to make the interpretation, etc. I'm sorry, how to do it in Python. We're not in R. A lot of statistics is done in R, but we're using Python. Okay, so let's take a look at the following example. A nursing home records data on the age and gender of its residents who have passed away in the last 5 years. The ages of the 12 female residents and 10 male residents are given below. Is there significant evidence of a difference in mean age of death for males and females at this nursing home population. Okay, so we set up our hypotheses, null hypothesis. Remember, your null hypothesis should always include equality. So we have the mean for females is equal to the mean for males. And then the alternate is that they are not equal, because the question didn't ask specifically, is there evidence females live longer? It just asked, is there a difference? Okay, so let's see how we could actually do this in Python. So here I've got a data set. Well, I have a list of all the female ages, and then I have a list of all the male ages. And then one thing that I'm going to use is I'm going to import stdev from the statistics package. And this is actually a little bit different than the standard deviation that we were doing, I think, in NumPy. That one was what's called a population standard deviation. And this one is a sample standard deviation, which just means you divide by n-1 instead of n. For a large data set, it's not a big difference, but for a small data set, it can make a difference. So this is kind of the appropriate thing to use to compute a sample standard deviation. Okay, and then here you can just see some summary statistics. So I'm doing the sample mean, sample standard deviation, and the sample size, first for the females and then for the males. Okay, and now we can actually run a test in Python. So if the scipy.stats package has a function called t-test, and this IND stands for independent samples. So this is an independent sample t-test. And you just input the two different data sets. So you just do t-test between, the female list and the male list, and it'll output both the test statistic t and the p-value. And so here we see the test statistic t is 3.4, which is pretty high. You can kind of interpret that as, okay, what we're observing is about 3.4 standard deviations above what we would expect if the null hypothesis were true. And then the p-value is 0.0027, which is very small. Okay, so with this small p-value, what do we conclude? There's kind of two different ways to say the conclusion. You can say you reject the null hypothesis, or you can say there's evidence for the alternate hypothesis. So what do we say? There's strong evidence that there is a difference in the mean ages. And in this case, females are the ones who are living longer. Okay, and if we wanted to run a one-sided test, we could have done that. And what it would do to the p-value, it would just cut it in half, okay? So if we had set it up as a two-sided test, our p-value would just be half. We get 0.001, because we would just be looking at the area in one side of the tail. But one good thing to keep in mind is that you should always decide on what your hypotheses are before looking at the data. So if you have reason to set up a one-sided hypothesis, then do so, but don't look at your data and then see which direction it's going and just set it up because of that. Okay, now you could also run this t-test from the summary statistics. So that would be with this t-test independent samples from stats or from the summary statistics. And in this case, you would just input, these things that we computed up here, the sample mean, sample standard deviation, the length, first for the females and then for the males. And then you can see that you're going to get the exact same answer here. Okay, p-value of 0.02. Okay. And then we've got a question. Does t-test independent return the values as a list? These right here? No, I don't think so. I believe the way we've set this up is it's just returning these, two individual variables named t and p-val. But maybe if we set this equal to, if you just called this as one variable, I don't know if it would return a list. It might. You could try it. Okay, I'll leave that for you to play with. Okay, So let's take a look at a two-sample hypothesis test for proportions. So, okay, so now let's assume we have two independent samples, but of a binary categorical variable. So not a quantitative variable like age or temperature. And we want to compare the proportions, i.e. the percents, with the two-sample z-test. So here, actually, we're going to be doing a z-test instead of a t-test because for proportions, we don't have this issue about approximating the standard deviation because it's specified exactly by the null hypothesis. Okay, so let's take a look at this example. So in 1954, polio was widespread and a new vaccine of unknown efficacy, I never know how to pronounce that word. Anyway, of unknown efficiency, I guess, or effectiveness was introduced. So to test whether the vaccine was effective, they took two groups of children, and one group got the vaccine and the other group got a placebo. And then they, kept track of which children got sick and which didn't. So here, PA and PB will be the proportions of the children, the PA being the proportion that get polio were given the placebo, and PB being the proportion that got polio that were given the vaccine. So if the vaccine is effective, what would we expect? We would expect that the percent who get polio that were vaccinated is smaller than the percent who got the placebo. And because that's what we're trying to show evidence for, we make that our alternate hypothesis, and the null hypothesis being that PA is less than or equal to PB. Okay, and let's once again pick a significance level of 1%. And so let's suppose that when they do this experiment, we get the following results. So we have about 200,000 children in each group, and in the placebo group, 110 got polio, and in the vaccinated group, 33 got polio. So you can see these sample sizes are pretty big. So we may expect that, that this is pretty significant evidence that the placebo is doing something. I'm sorry, that the vaccine is doing something. So let's quantify that in a hypothesis test. Okay, so the function that you want to use for this is called a proportions z-test, which you can import from stats models. And so here you just kind of input the summary data, like the counts and the sample sizes. So here our counts are 110 and 33 sample sizes, about 200,000 for each group, and then run the proportions z-test on those counts and sample sizes. And what do you see? If you just run it without further input here, it's going to default to a two-sided hypothesis, and it will compute this p-value right here, which is tiny, tiny, tiny. Technically, if we want to get the p-value for a one-sided test, the way we set it up here, we would want to take this number and divide it in half. So we want to cut in half the p-value from the two-sided test to get the one-sided p-value. But in this case, they're both essentially zero. So we see very strong evidence that the vaccine is effective. Yes, so and then we've got a question here. Can you remind me what the difference is of one-sided versus two-sided in application, i.e. what that means in this context? Okay, yeah, so in this context, I would say it's very natural to set up a one-sided alternate hypothesis because you're investigating the effectiveness of a vaccine. So you're kind of, you're kind of assuming that it's not going to make things worse. So it seems reasonable, that's your whole hypothesis from the beginning of doing the study is you're investigating whether the vaccine is effective. So you're investigating that this percent is smaller than that one, but it would not be appropriate in a context where a priori you have no knowledge of whether there would be a positive or a negative effect of an action. So in that case, if you really, had no reason of knowing whether the effect was going to be to increase or decrease something in an experiment or in a treatment, it would be most appropriate to set it up as two-sided. Hopefully that answers your question. Okay, good. Okay, so, and then in the homework, you'll be looking a little bit at A/B testing. So I'm not going to talk about this a lot, but I just want to kind of, give a little introduction here to what we're talking about. So A/B testing is a method of comparing two or more versions of an advertisement, web page, app, etc. So for example, you can think about Amazon is trying out if they want to change the display of their homepage. And so they make like a small adjustment to the display. Maybe they add a little, button, or they add a picture, or they do something different, and they direct a small amount of their traffic to the new version of the site. And then they keep track of the behavior of the customers who got that new version, and they compare against, the behavior of the customers who got sent to the regular site. So this happens more and more these days. This is kind of going on all of the time. So in a lot of ways, it doesn't make sense to talk about, the Amazon website, because there may be many different versions depending on which one you're directed to. But this has become really standard for making business decisions, testing out, based on internet traffic, a lot of these different hypotheses about what will help and what will hurt. And this was used extensively by President Obama in his 2008 and 2012 campaigns. So for a lot of different things, so to optimize fundraising strategies and, get out the vote program. And so check out this Wired story if you haven't read it already, and also these episodes. It's quite interesting. Okay, and so I think, so for example, what does this mean? Let's say you have a company who's developing an advertisement, and you basically have two options you can go with, ad A and ad B. These are like our two different populations. And so you want to figure out which one is better. So you use your Google Ads to randomly show 1,000 internet users ad A, and 1,000 get ad B, and then you compare the difference in their behavior. Okay. I think that kind of wraps up what I wanted to say to kind of wrap up hypothesis tests. Any other questions on the hypothesis tests before we move on to time series? Okay, very good. All right, so go back to the beginning here. Okay, so for the rest of today, we're going to be talking a little bit about temporal data analysis and specifically applications to the stock market. So this is kind of a fun application of data science that you might not see in, introductory courses necessarily, but it's a fun thing to play with. And if you're interested in it, could be something you explore further in your projects. Okay, so what do we mean by temporal data analysis? Often referred to as time series analysis. So this is just data that's been collected over time. So we can think about a stock whose value is changing in time. We can think about, the weather as it's changing in time, temperature. You can think about even things like a book, right? If you want to think about the letters that spell out every word in every sentence in a book, there's a natural order there, which makes it appropriate to think about, those written letters as a time series. Okay, so there's lots of different applications for this. We'll focus today on stocks and mathematical finance. And some of the things that we'll talk about will be, just how to do this in Python, how to import stock data using the Pandas Data Reader package, and then how do we visualize things appropriately, how do we compute rolling means, and then we'll talk a little bit about doing some frequency domain analysis. Okay, so mathematical finance used to be considered somewhat boring, and this was mainly because most of the financial instruments of the day were kind of boring. They were just loans and other pretty simple financial instruments. But since the 1980s, this has really changed a lot due to deregulation in the financial industry, and also a lot of new ideas and developments coming out of math and computer science. So this has turned into actually a very sophisticated industry with very complicated models and strategies for making decisions. So for example, the Black-Scholes model uses very advanced mathematics to model the financial world. And you have many algorithms that are responsible for making split-second decisions. And so machine learning and data mining techniques have become very popular and more important to the industry. For example, high-frequency trading is one branch where you make thousands of trades in a short period of time. And this can cause problems. So there have been some flash crashes, as they're often called, in 2010 and in 2013, where due to kind of the predictive performance of an algorithm or strategy, it caused a real impact in the market. So in 2013, there was a fake tweet. Well, there was a tweet about a fake attack on the White House, which caused this very rapid crash. It recovered, but still, you sort of see how sensitive these strategies can be to various inputs. Okay, so first of all, installing the Pandas Data Reader. This one is not included in the Anaconda distribution, so you'll need to do this separate installation. So do that before you try to use it, just a little pip install Pandas Data Reader. And then here, we're going to import all of our usual packages, plus a few more, like the Pandas Data Reader and DateTime, and also this periodogram function, which we'll talk about at the end of the lecture. That's for the frequency analysis. Okay, so the Pandas Data Reader package, I guess there's two different functions available, which is pandareaders.data, pandareaders.wb. We're going to be using the pandas data reader.data. And these extract data from various internet sources into a Pandas data frame and making it actually really easy to get this data into Python so that you can. So here are some of the sources that are supported by this function. And most of these are financial-based data sources, but I think not all of them. Okay, and so how do you use the function? Well, the basic syntax is, you do pandas data reader.data reader, because that's not at all redundant, but that's what it is. And then you want to specify your name, your data source, your start, your end, and then some other things that are optional that you probably won't need. but maybe you will, depending on what you want to do. Okay, so first of all, the name of the data set that you're interested in. With stocks, you want to specify what stock you want to retrieve, Apple, Google, etc. The data source can be a string or it can be none. So here's some examples of different data sources that you can input into the function. And then, because time series data can go on for a very long time and you may not want to look at all of it, it's quite, it's helpful to, just pull out whatever chunk you're interested in. So you always want to input a start and an end, although this will default to 2010. By default, it'll take data from 2010 to today. Okay, and if you're interested, you can always check out the documentation for further information and further options on the import. All right, but let's get some data to look at. So let's kind of go look at a 10-year period from 2010 to 2020. We can use the datetime function to format this appropriately. And then we can use the data reader function. And let's pull some Apple stock. The data source here is Yahoo. And we have our start and our end dates that we're interested in. And so you can see what the resulting data frame is here. We have the dates here in the first column, and then we have a couple of things. We've got the high, that's the highest value of the stock on a given day, the lowest value on a given day, what the stock opened at, what the stock closed at, volume, so how much total trading there was of that stock, and then the column that we're going to be most interested in for today's lecture is the adjusted closing. So this is a little bit more helpful than just the closing value, because this adjusts for, if a company decides it's just going to, what do they call it? Do a stock split. So where you just kind of split half the price and double the number of stocks, that'll really throw off the patterns that you're seeing. So this adjusted close data adjusts for that. Okay, and then we have a question here. How does Python get these data? So that's a good question, and I guess I'm not sure exactly of the nuts and bolts of how it works, but these, I don't know if Alex wants to jump in and make a comment here, but these data are stored in various databases by various companies, but it's publicly available. So it basically just, I guess it's a function that, builds in where to go look for the data. And then there's a lot going on behind the scenes about how it actually extracts that from the various databases. And that part I'm not so sure about. Okay. Okay, so let's see. I think we went over kind of what these guys are. So let's take a look. So we pulled some Apple stock. If we want to visualize it, we can just do a basic plot. So this is a plot of the Apple adjusted close. And well, we see overall very positive trend, stock going up in value. Of course, we might be interested in making comparisons. So maybe we're debating between a couple of different stocks that we want to buy. So let's see, let's get some more data and do some comparisons. Okay, so in addition to the Apple data here, we're also pulling data about the Microsoft stock and the Google stock. And what we're doing here is actually making a tuple like we talked about a few lectures ago, but it's outputting into these specific data objects. Each of these is now its own data frame. So the output is not a tuple. The output is just 2 additional data frames like the first one we computed. Okay, and then we have another question. Is it possible to use machine learning to predict a stock price? Yes, yes, it is. So there's, lots of different strategies and different competing ways of doing that. But yeah, I mean, I think there's lots of ideas based in machine learning that could apply to predicting a stock price for sure. Yeah, I mean, and today we're talking more about making, sort of analyzing this time series data. But of course, there are a lot of other factors. You might be interested in looking at what's going on in the economy and what's going on in politics and a lot of other kind of historical data. And so it is of interest to build more complicated models that take these various factors into account. Okay, so here let's look at our additional. So we created these additional data frames, but now what we want to do is we just want to extract the adjusted closing column from each one and make a new data frame that just has adjusted close of these three stocks, Apple, Microsoft, and Google. So we define this new one, and you can see here, okay, it's made now a single data frame containing the adjusted closing of the three stocks. And if we want to plot this, we can just use the built-in .plot function, which is easy. We'll talk a little bit though about how this might not be the best way to visualize it. But we can see Google and Microsoft and Apple. Okay, so plot's very easy to get, but it's a little bit difficult to read. And it's a little difficult to read just because the Google stock has so much larger values than the other two that it appears a lot more volatile. It looks like it's going up and down a lot more, but it's not really, but that's not necessarily really the case. It's just that, we're plotting the absolute price. We're not looking at the relative change, but the absolute price doesn't really matter. What matters is whether it's going up or down. So we really are usually more interested in the relative change of an asset rather than its absolute price. Okay, so one thing that you can do to try to look at this at different scales is to use a different y-axis for some of the stocks. So what we can do here is use one y-axis for Apple and Microsoft, because those are real small, and then use another axis for Google. So here we define a secondary y-axis for those two. And so you can see, okay, this is our Google axis. This is our Apple and Microsoft axis. Now this is a lot better, so we can visualize how these stocks are changing in time a little bit more easily and compare the volatility a little more easily. But of course, that works okay for like 3 stocks, but let's say you had 50 you wanted to compare and they were all at different scales. That wouldn't work so well. So we kind of need a different procedure to be able to plot this. Okay. So a better solution is to just define everything in relative terms. So we want to define and plot the stock return since the beginning of some period of interest. So maybe since the beginning of the year or since the beginning of 2010, depending on what you're interested in. So we'll define the return at time t to be the price at time t over the price at time 0. So for example, if this number was like 1.2, then you would see that the stock had increased by 20% since the beginning of the period. Okay, so to do this, we need to transform the data, which we can do with the lambda function. So So what we'll do is define a new data frame, stock return, which we'll get from our adjusted close data frame, applying this lambda function, which maps the series x to x divided by its initial value. Okay, so you can see now this data frame, it's going to start at a value of 1. And now we can interpret these values as, showing like the percent of the initial at time t. Okay, so now let's take a look what happens if we plot this stock return, and we can also add a little baseline here at 1. So you can see this is the baseline that we're comparing against. And this is a really helpful plot for comparing these 3 stocks. And now everything is on the same scale. And so you see that it looks like, Apple is outperforming these other 2 stocks, even after the normalization, which is a little bit different than the conclusion you might make. If we first just glance here, it kind of looks like, oh, wow, look at Google. But once we do the appropriate normalization, we see that Apple is outperforming it a bit, even though it's more volatile. Okay. All right, and there's a few other ways that you can plot it, a few other ways that you can, this is more about keeping track of the change from some initial point in time. But you might also be interested in seeing daily change. So one way to do that is to look at the percentage increase of a stock. So the increase at time t would just be the daily change divided by the starting price. Okay, so the difference between what we did before is we were looking at the percentage change from the very beginning, but this is, looking at the daily percent change. Or you could look at the log difference. So you could define the change at time t as the log of the price at time t and over the price at time t minus 1. And using those lovely properties of logs that hopefully you all learned in, I guess, pre-calculus, you get the difference of the logs. Okay, so this has a nice property. So if you sum up all of the log differences, you'll get a telescoping series where everything in the middle cancels, and you just end up with, the log of the price at time t minus the log of the price at time 0. And so that's kind of a nice property because you can interpret it in terms of the total change. And it's a little bit useful for making some connections with modeling stocks in continuous time. Okay, so let's take a look maybe at what this looks like if we plot the log differences. So here we're going to, again, take the adjusted close data frame, and we're going to apply a lambda function, but this time we're going to apply the lambda function that maps the data series x to the log of x minus the log of x shifted by 1. So this shift function moves the dates back by 1. And then we can take a look at what we get. There won't be any data available for the first day because you can't compute the daily change if you have no history. But then for every day after that, you'll see this log difference for the daily change. Okay, and then let's see, we got a question. Why is it not price t minus price t minus 1 over price t minus 1? You could do that too. So like both of these are interesting things to look at. Okay, this what was written in the chat. Oh, I see. So why you mean for defining the index of t, why is it not price t minus price t minus? I believe it should be actually. I believe that's a typo. If the change is small, there won't be a big difference. but I think you are correct that this more correctly should be a t minus 1. So sorry about that. Yep, good catch. Okay. So we defined the stock change by the log differences, and now we just want to take a look at the plot. This one's, it looks kind of chaotic, I guess. You got all these spikes everywhere, but we see the daily change in terms of the log difference, and it looks like, what useful conclusions can we draw from this plot? You can certain periods of time, certain years, certain periods of time where you have greater volatility. So that's kind of interesting, and it may be interesting to look at like these maxima where you can see, what are these extreme values? What's the difference in the extreme values of these daily changes that you see in the different stocks? So yeah, there's some interesting things to be analyzed. Okay. So pros and cons, right? Looking at the returns since the beginning makes the overall trend a lot easier to read, but the log differences emphasize, the daily change, which can also be useful, especially if you're thinking about, difference between long-term and short-term strategies. If you're doing like a real short-term strategy, the daily change may be quite important. Okay. So what we looked at so far was comparing, oh, wait, I sort of lost track of time a little bit, but it's definitely time for our break. So why don't we take our 5-minute break? So it's 1:08 right now, and we'll come back at 1:13. So take a little stretch, and I'll see you in 5 minutes. All right, let's go ahead and get started after the break. Okay, so one thing that's often really helpful to look at when you're given a time series is a moving average. This is especially helpful for time series data that's kind of noisy. You know, if you have a lot of noise or a lot of short-term fluctuations that don't really contribute to the long-term pattern, it can be helpful to, instead of looking at XT directly, look at a Q-day moving average. Okay, so how do we define this? We define this moving average at time t based on the previous Q days by just taking the average of x of t for the previous Q time values. And we can do this with the rolling function in pandas, and then also sort of get a nice plot of this movage. So let's try this. Let's create a 20-day moving average for the Apple stock data that we were looking at previously. Okay, so you may remember that I had my Apple data frame and it had all of these columns, high, low, adjusted close. So now I'm just going to add an additional column called 20-day, which is going to be my 20-day rolling average. So I'm going to take the adjusted close column and I'm going to apply the rolling function with a window of 20. So that means I want to go back 20 days and a center of false. So if you have center true, it's going to take an average of like the 10 previous points and the 10 points after you. But if the center is false, it's going to take the mean will be computed just from the time points in the past, which is appropriate for stock analysis because you don't know what's going to happen in the future. So here you would always want to have this center equals false. Okay, and so we see here, now we've got this extra column, which gives us our 20-day rolling average. And that's not possible to do for the first 20 days because you don't have 20 days worth of data to compute it with. So our first value starts here, which is the 21st row. But then we have all of these values for the rest of the data. Okay, and of course, you know, the bigger the window that you choose to compute your rolling average, you know, the more data you won't be able to compute at the beginning. So just one thing to keep in mind. Okay, so now if we make a plot of the adjusted close together with the 20-day average, we can see that this average, you know, exhibits a lot of the same patterns as the red curve, but it's just kind of nice and smoothed out. So this kind of makes some of the long-term trends a little easier to see. Okay, so one thing to keep in mind, so this is really nice. We've kind of smoothed the curve. Now, the bigger you choose Q, the more you're going to smooth that curve out. And so that can be both good and bad. It's nice to have a smooth curve, but if you smooth it too much, you may wash out all of the signal in it. So there's a little bit of an art here to how much you want to smooth it out. Okay, so let's see. Yeah, so it can make it easier to identify trends. The larger, the less responsive. It will be to fast fluctuations. So it's a good way to get rid of noise, but you don't want to go too far or you'll wash out your signal. Okay, so let's take a look so we can kind of visualize this at the difference between a 20-day and a 50-day and a 200-day moving average. So here we're going to do the same extraction. We're going to create two more columns with a 50-day and 200-day average, just like we did before. And if we plot these, you can see now here we have, the noisy data in red, and then the blue curve is the 20-day average, the purple curve is the 50-day average, and the gray curve is a 200-day average. Okay, and of course, yeah, the 20-day moving average is the most sensitive to small fluctuations, and the 200-day moving average is the least sensitive, but also kind of fails to capture maybe some important changes that you would have liked to know. Okay, so now that we're kind of equipped with some basic tools for plotting, we can talk a little bit about trading strategies and backtesting. So trading is the practice of buying and selling financial assets for the purpose of making a profit, right? Basic idea is you want to buy low and sell high. And there's many different strategies that you can use to help you decide when to buy and when to sell or to make a profit. And they can be very complicated strategies, but not all of them are very complicated strategies. One example that is kind of, we can very easily visualize from what we've done so far is called the moving average crossover strategy. So this strategy is based on two moving averages, a fast one and a slow one. And the strategy is you want to buy the asset when the fast moving average crosses over the slow moving average, like on the way up. And then you want to exit when the fast moving average crosses over the slow moving average again. So let's try to visualize that back here in our plot. Let's take the 20-day as being the fast moving average and the 50-day as being the slow moving average. So we want to buy when the blue crosses on top of the purple. So according to that strategy, we would buy right here, and then we would keep the stock all the way until this point, right, when the blue crosses back under the purple, and then we would sell here. But that's pretty good strategy, right? Because we would have bought here and then sold here. So we would have had a nice profit from that. Okay. So, right, so this is the outline actually of a complete strategy that you already have the tools to try out. And an important thing to do before you actually go out and buy stocks based on a strategy is to do what's called backtesting. So you want to take historical data and you want to try out your strategy and see what would my profit have been if I had employed this strategy on historic data. And that will give you a better idea of how you can expect the strategy to do in the future. Not a perfect idea, but a decent idea. Okay, and let's see, we have a question here. Could the opposite be done for shorting a stock? I assume so, but I will confess I don't know a lot about stocks and shorting of stocks. But I am inferring from the question that you kind of want to have like, you want to infer the opposite, right? Okay, I don't know if anybody has any comments on that. Yeah, I guess I would assume so, but I don't know much about shorting stocks. Okay. Okay, and so so regarding the back testing, now you can write Python code that can actually implement and back test a trading strategy. But there are also lots of Python packages that are already written for this. PyFolio, Zipline, Backtrader. Okay, so you can kind of do this from scratch, or you can utilize some of the packages already out there. Okay, so I think this is going a little faster than I thought, so that's good. I don't think we're going to run out of time today. So now let's talk a little bit about time domain versus frequency domain analysis. So frequency analysis is something that math people tend to really love, but is actually really useful in the analysis of time series. So what's the basic idea? We have our time series, x of t. T is the time domain, but a lot of times it's helpful to map the signal into the frequency domain. So for example, let's say we have the function x of t, which is the cosine of 2 pi times ft. You may remember, again, from your pre-calculus class, that this function has a period of 1 over f, which means it has a frequency of f. So this f, determines the frequency of the function, which is just how rapidly the function oscillates. Okay, according to Fourier analysis, we can actually decompose any signal into its frequency components. So if you take a signal that's defined on a finite interval like 0, 1 or 0 pi, you can write it as a Fourier series. So remember that this e to the 2 pi I and t, this is just the sum of sines and cosines at this frequency n, and you can write it as the sum of these sines and cosines weighted by the appropriate Fourier coefficients, which are usually denoted with a little x hat. So x hat denotes the either the Fourier coefficients or the Fourier transform, depending on what setting you're in for a function that's defined on the whole real line. It can be expressed in this way. So kind of in the same way as a Fourier series. Now you're just kind of using an infinite number of these functions, but they're combined together with the Fourier coefficients. Okay, so one thing that you can look at is the distribution of the frequencies, right? So you can obviously look at the signal in the time domain, and that will give you spatial information. But if you map it into the frequency domain, it's useful to think about which frequencies have a strong response, where are these Fourier coefficients large, and which frequencies have a negligible response, meaning they don't really contribute much to the signal. The signal doesn't really have those frequencies. And one way to do that is to look at what's called a periodogram. So this is just the square of the magnitude of the Fourier coefficients. Okay, and so you can think about why this is useful, because there are lots of time-dependent signals that are periodic, or at least parts of the signal are periodic. So for example, if you think about sunspots, these happen in an 11-year cycle. And so, you would, if x of t is your time series representing the strength of the sunspot, you would, expect to see a large Fourier coefficient for a frequency of 1 over 11. Remember, the period is 1 over the frequency. Or you can think about temperature. Temperature is very natural, and temperature is interesting because you have different kinds of fluctuations. You have yearly fluctuations from the seasons, but you also have daily fluctuations. And so that's a good example of where your overall temperature, it's good to represent it as like the sum of two different frequencies, one that's like your yearly frequency, and then one that's your daily frequency. So a signal can have, multiple frequencies that come into play. Okay, and so to illustrate this, we're going to kind of follow some course notes from James Holland Jones on time series, and we're going to look at some measles data from New York City. So first, let's read in the data. So we're going to use our pandas read CSV function, which as you saw on the last homework, makes your lives a whole lot easier. And so yeah, we don't have to do a whole lot here. We can see that we get the date and the number of cases of measles. Okay, and I think you can see here, the date imported like a little weird, but these are basically monthly measurements. So this is 1928.0 and then 0.08, but you see there's 12 of these before you get to 1929. So we have monthly measurements starting in 1928. Okay, so let's take a look here. If we get a plot of these cases, you see lots of spikes, and they seem to be kind of equally spaced. There definitely seems to be some strong oscillation, some strong frequency patterns in this signal. And we could try to think about, what kind of frequencies we would expect for measles data. Probably for data, it makes the most sense to think about yearly spikes due to seasonal changes. Cases of flu tend to spike, in the fall and the winter. It's probably a similar phenomenon for measles. Okay, so we observe these regular periodically spikes that seem to appear about once a year, kind of matching with your intuition of how that type of outbreak would fluctuate. But let's see how we can actually make this precise by mapping into the Fourier domain. So if we compute the power spectrum, we can see which frequencies make up this time series. Okay, so here we want to actually extract the values from the cases column. So cases will just be the df cases.values, and then we'll make a periodogram from those values. What we want to do here is tell it how many measurements per time unit we have. Because we have monthly measurements, we're making an observation 12 times per year, so we'll put a 12 there. If you don't do that, it's okay, but you just have to be careful about how you interpret your units without that there. Then your underlying units would be months, not years. Okay, and now let's take a look at the periodogram. So you can see that there are a number of different frequencies in this data, but you see a really strong response at 1. Yeah, so we have a really strong yearly frequency in this data, and then we've got some smaller frequencies and a few larger frequencies, and then after about 3, it just kind of tapers out. Okay, so since there are 12 months per year, we set the measurement frequency argument to 12, as we discussed, and it's natural that this is a year. Okay, so one question that's kind of useful to think about or look at is, why is this type of analysis useful for stock data? Why or why not? Does anybody have a thought on that they want to put in the chat? Okay, nobody does. Oh, we've got one. Thank you, Conrad. If you have a fluctuating stock, you would be able to determine when it is best to buy, sell. Exactly, right? So you may observe like consistent patterns, maybe things, maybe there's like a around the holidays, stocks tend to go up. And then in the new year, I actually don't know if that's true. I'm just making a guess here. And then in the new year, they go down. So there should be, definite patterns, temporal patterns that you could utilize in when to buy and sell. And then we have another comment. You could try and correlate it to certain events in the world or events in the company. So that would also be useful to look at, not just what's happening in time, but outside factors will play a huge role. Okay, so we still have 10 minutes because that didn't take as long as I thought. So I see two options for the last 10 minutes. I can go over the confidence intervals with you that we skipped, since we actually have time for that, or we can do breakout groups and you can try, so as an exercise in the breakout groups, you can try looking at the Apple stock and actually a periodogram for the previous 10 years and looking at what type of information, what type of frequency information you see in the Apple stock. So who votes for confidence intervals? And I will say that exercise though won't be graded because I didn't get it together ahead of time. So that would be, for fun. Who wants to do confidence intervals and who wants to do breakout rooms? So maybe just type in the chat what you prefer and I'll hopefully get a sense. Okay, everybody wants to do confidence intervals. Nobody wants to do breakout rooms. Okay, I am seeing a really resounding vote for confidence intervals. Okay, so since that didn't take as long as I thought, let's go back and I'll go over the confidence intervals with you in the last few minutes. Okay. Okay, so confidence intervals are very important in statistics and different from hypothesis tests, but the idea of statistical inference is the same. So instead of setting up, a hypothesis about population parameter, we want to estimate that population parameter. We're never going to know it exactly, but we're going to come up with basically a range, an interval of values, and we're going to say, well, we have pretty strong evidence, or we're pretty confident that the population parameter lives somewhere in that interval. We don't know exactly where, but we think it's, maybe we're 95% confident it's between 2 and 4, even though we don't know what it is. That's the basic idea of a confidence interval. So we're going to collect data. We're going to start with a sample. Here, I'm just going to be talking about a one sample confidence interval, even though confidence intervals based on 2 samples are also quite important. But let's just start simple for the one sample case. And let's say we've collected data and we want to get an interval estimate for the population mean. So let's take a look at this example, which is ergonomic keyboards. So a study is conducted to estimate the preferred height for an experimental keyboard with large forearm wrist support. A sample of 31 trained typists was selected, and the preferred keyboard height was determined for each typist. The resulting sample average preferred height was an X-bar of 80 centimeters. Sorry to be consistent with my notation in the previous lecture. I should have made that a little X-bar because I was using little X-bar for an actual sample mean. So make that a little X-bar. Assuming that the preferred height is normally distributed with a sigma, a population standard deviation of 2 centimeters, obtain a confidence interval for mu, the true average preferred for the population of all typists. Okay, so let's kind of remember what the CLT tells us. The CLT gives us really useful information on the distribution of the sample mean X bar. And it tells us that the sample mean is approximately normally distributed with an expected value or mean mu, the true population mean, right? So the expected value of the sample mean is the true population mean, and a standard deviation of sigma divided by the square root of n. So this is why a large sample size is so helpful, even though the expected value of the sample mean is always mu. The larger your sample size, the smaller the standard deviation, meaning you can estimate that mu more and more precisely with a larger sample size. Okay, so we can standardize the sample mean just like we did when we were conducting a z-test. So what do? We define our standardized variable z by taking the sample mean, subtracting the mu, and dividing by sigma over square root of n. And so since z, now I will say, right, we don't know mu, but bear with me for a second. Since z is a standard normal variable, what do we expect? We expect the integral under the standard normal curve between minus 1.96 and 1.96 to be 0.95. Now, I don't expect you to know that off the top of your head, but you can check that if you take a standard normal distribution and you look at what are the cutoffs where I get exactly 95% of the area of the bell, then you can check that those are 1.96 and minus 1.96. So let's just assume that we know that. Yeah, how did we get 1.96? Exactly. We basically just assume that we already know that for a standard normal distribution, if you look at, this is kind of related to like a little rule of thumb where you have about 68% of your data within one standard deviation, and you have about 95% of your data within two standard deviations, and about 99.7% of your data within three standard deviations. So this is just kind of a known fact for the normal distribution, but you would have to look it up, or you would have to, know that. And it's actually more precisely, it's not 2, it's 1.96 is the more precise number. Yes, 1.96 is specific to the standard normal variable z, not the problem. Indeed, yeah. So that would be, so it's illustrated here, right? So where is this 1.96 coming from? It's coming from, if we take a normal CDF, this is for a standard normal distribution, evaluated at 1.96, and then minus a standard normal at minus 1.96, we get 0.95, okay? And that is specific to the standard normal distribution. But what we want to do is we want to set a confidence level for our confidence interval. We want to make a 95% confidence interval or a 99% confidence interval. We're going to decide ahead of time on the confidence level that we want for the interval. And let's say we've decided we want a 95% confidence interval. If we've decided we want a 95% confidence interval, then that means we need to use these numbers, these 1.96 numbers in the construction of the interval, and likely how that's going to come into play. Okay, so what we see here in this calculation is that if z is a standard normal random variable, then the probability that it's between minus 1.96 and 1.96 is 0.95. Okay, we see that here. So let's take this standardized value of the sample mean, and let's restrict it to be between minus 1.96 and 1.96. And here we're going to do a little rearranging to kind of derive something interesting. So if you do a little algebra, you can see that this inequality is actually equivalent to this inequality. So this is equivalent, you just have to manipulate it and rewrite it to mu being in between sample mean plus 1.96 sigma over the square root of n and sample mean minus 1.96 sigma over the square root of n. So even though we could not actually compute the value of z because we don't know mu, we can use this procedure to flip it around and get a range of values for mu, because note, this upper bound you can compute, right? This lower bound you can compute. You know the sample mean, and you can approximate sigma, or maybe they tell you in the problem, and you know n. And this is what the interval is, okay? So then you say, all right, my confidence interval, I'm going to construct by taking the sample mean and minusing 1.96 sigma over the square root of n. Sigma over the square root of n is often referred to as the standard error. And I can say that I'm 95%, that this is a 90, let me make sure I say this in the correct way. You would call it a 95% confidence interval. And what that means is this, if I repeat this procedure, I get data, I construct this interval, and I do that over and over again. 95% of the time, the interval will contain the true mu. So that's what we mean by 90% confidence. Okay, right, and so just be careful. It doesn't mean that there's a 95% chance that the true of mu lies in the interval, even though I know that sounds very similar. That's not exactly what it means, but it means if you repeat this procedure over and over and over again, 95 times it's going to work. So that's the subtle difference. Okay, and then we have another question. Sigma is still estimated by S. Yeah, in practice, in this problem, they just told it to you. And it's basically assume the population standard deviation is 2 so that you know what to plug in. But in practice, you don't really know the sigma. So, so a lot of times you have to approximate it with S. And then this sort of turns into a confidence interval based on the t distribution instead of the z distribution. But we won't really go into that because we're just giving the basics here. So there's a similar procedure you can do where you have a t distribution instead of a standard normal distribution, and that's a little bit more precise because you can do it with the S. But for this class, it's okay to just think about approximating it with the S. Okay, so I guess I went 2 minutes over. Sorry about that. So feel free to sign off. If anybody has any additional questions, though, I'm happy to answer them.
So just to clarify, if we wanted to say find like a confidence interval of 75%, then we would change negative 1.96 and 1.96 to like a corresponding like smaller value, whatever that like is for the standard normal variable.
Yeah, that's exactly right. Yeah, that's exactly right. And you're going to have a trade-off here. So you would like to have a small interval because a small interval is going to be a more estimate for mu.
Right.
But the smaller you make the interval, the lower the confidence is going to be, So like you're saying, you could make a smaller interval, but then you would only be, say, 75% confident. So
Right. Well, and this interval already, I mean, maybe it's just because it's centimeters, but this interval already seems to be pretty small, around 80 centimeters. Like it seems pretty precise, but I could be wrong.
Yeah, and that depends totally on the application and really what the amount of variation is. If you think of this as kind of small or big, it's, but to me, it does seem pretty small, given that the standard deviation is 2, that it's, narrowed in on it a lot.
No, yeah, it is. Oh, well, yeah, I guess, yeah. Okay, awesome. Well, thank you.
Yeah, thanks for the question. All right, everybody, have a good weekend. See you later.